We're given this equation and we're told that there's a point of inflection when x is equal to 1. So a point of inflection is when the second derivative changes sign. So that is going to be the first thing to find in this question. The first derivative followed by the second derivative. So I've got 2 ln k minus 3x. That's going to become 2 over k minus 3x when I differentiate. And I need to use the chain rule and times by the derivative of the inside. So I'm going to times by minus 3. You can do the chain rule in full, but ideally you want to learn how to do kind of we call it the outside inside rule. Deal with the outside, which is just ln, so we get the 1 over. Of course, we times by the 2 as well, and then we times by the derivative of the inside. Then it's plus 2x minus 3. Okay, just tie that up. So it's going to be minus 6, and I'll write it as k minus 3x to the minus 1 plus 2x minus 3. Right, second derivative. Same idea, so I'm going to times by minus 1 when I differentiate this, like times by the power. The outside is something to the power of minus 1. That's going to give me 6, and then I'm going to times by the derivative of the inside, which is a minus 3 again, so I'm going to get minus 18. K minus 3x to the minus 2 plus 2. And I could write that as 2 minus 18 over k minus 3x all squared. And I found the second derivative. Onto the point of inflection part. So a point of inflection is when the second derivative changes sign. An example is y equals x cubed. For x less than 0, the gradient itself is decreasing. The function is, in fact, concave. And then after x equals 0, the gradient starts to increase and it's convex. There's a point of inflection at x equals 0. And momentarily, the second derivative becomes 0. Now, this is basically accepted in A-level that you always do that. I just want to point out that it's not always true. You can get a function like y equals the cube root of x, and then the function is actually convex followed by concave. The gradient's increasing and then it's decreasing. However, at x equals 0, the gradient itself is not defined, and so nor is the second derivative. So the second derivative manages to change sign without ever equaling 0. I just want you to bear that in mind. I talk about this in all my videos on points of inflection because I feel like even though it goes a bit beyond the syllabus, it's important to be aware of. Well, for this question, we're going to look at when x equals 1, and then we're going to look at when the second derivative actually equals 0. So it's going to equal 2 minus 18 over k minus 3 all squared. And then we're going to seek a second derivative equaling 0 at the point of inflection. Then we're going to get 2 equals 18 over k minus 3 all squared. Rearrange to k minus 3 all squared is going to be 18 over 2, or 9. Therefore, k minus 3 is going to be plus or minus 3. K is going to be 0 or 6. So in fact, those two values of k would give us a point of inflection x equals 1. We're told that k is a positive constant, so we can just reject this one and take k equal to 6. So it is also given that the curve intersects the x-axis at exactly 1 point, and we're asked to show by calculation that the x-coordinate of this point lies between 0.5 and 1.5. So I'm going to let f of x equal this thing here, and I'm going to substitute 0.5 and 1.5 in and seek a sign change. I could maybe just stick with y, but I quite like the sign change rule tends to say if, it refers to f of x. So f of 0.5 Just substitute those values in. But now remember we're replacing k by 6. Let's get 1.758. Do the same thing, but just replace the 0.5 by 1 everywhere. Minus 1.439. So there is a sign change. That is normally deemed to be enough, but we should also technically add the function is also continuous over the interval. Actually, it's continuous everywhere, so I'm just going to leave it like that. Function is continuous. So there is a root between. Technically, there could be more than one root, but we are told that it just intersects at one point. But that's what the sign change rule does. It shows you there's at least one root. The reason being is that we've got our graph here, and I've shown for 0.5 it goes below the axis. I don't know why I'm doing it there, here. And then at 1.5 it goes above. So because it's continuous, it doesn't jump. It must at some point hit the x-axis, and that is going to be our root. The reason it has to be continuous is that you could get something like 1 over x, and then you get it jumping from negative to positive, but it never actually crosses because it jumps the discontinuity. So that's just something to be aware of. Anyway, that's enough for this part B. Okay, so let's calculate this root, and the question's asked us to use the Newton-Raphson method. I'm just going to very quickly talk about where the Newton-Raphson method comes from. So let's say you've got a function that looks a little bit like this, and we want to find the root. Well, what we can do is we can put in a value x naught as our starting value, and then imagine drawing a tangent to this point. Goes a little bit like this. I'm trying to not exactly, okay, actually it would go below, wouldn't it? Maybe hit here. And then this would be a new value, x1. And then we can do the same again, draw a tangent, and so on. And you actually see that if we follow this path along, we're going to converge towards the root. So what is actually happening? Well, we've got f of x, so this is f of x0, that's the rise. And then this is going to be x0 minus x1. So the gradient will be f of x0, the rise, divided by the run. However, that's the gradient of the tangent, and it will equal the gradient of the curve at that point. So f dash x gives you the instantaneous gradient along the curve. If you then put in x0, that's what this means, then we get the gradient at that point. I can times through by x0 minus x1 and then divide by f dash x0, basically swap these two around. Then rearrange to give x1 is x0 minus f x0 over f dash x0. And that gets us a second point that's closer. And if we just then repeat that and repeat that, we got an iterative method to converge towards a root. And the general formula is then given by this. We just use xn and xn plus 1. So this is our, this is a point, and then this is the next point. So you put in x0 first to get x1, then you put in x1 to get x2, and so on. So, okay, that's, you don't have to be able to derive it yourself for A level, but I think it's good to just refresh and see where it comes from. So remember, this is our f of x, and we actually found f dash x earlier on, right at the start. Here it is. So then the Newton-Raphson method becomes xn plus 1 is going to equal xn minus 2 ln, remember k was 6, 2 ln 6 minus 3 xn plus xn squared minus 3 xn. All over this derivative. How should I write it? Okay, I'll write it as 2x minus 6. I'm going to leave it as a negative indice. Sorry, that should have been 6 because we've upgraded that. Rather than having fractions within fractions, I'll just write it like that. And then minus 3. Sorry, there should have been little n's here and here. Right, we've got our starting value. We're going with 1, which is in between the 0.5 and the 1.5. Why not? Midpoint. And then we just got to, so we put 1 equals, so it's stored into our answer button. This can be the thing that varies. Just very carefully write this formula out with xn replaced by answer. Nearly there. Okay. So we get x1 is 1.0657. We're being asked to give our answer correct. Oh, sorry, each iteration correct to 5 decimal places. So I've only got 4 at the moment. So I need 4. This is actually going to be 4 or 5. Oh, sorry. Yeah, so it's going to be 4. Then we've done all the hard work. Just press equals again to get the next one. 1.06568. And we'll keep going until it stays the same. And in fact, it has. Okay, brilliant. That's all we need. So I think I'll just say that x is equal to 1.06568 as my answer. Nice. Finally, by choosing suitable bounds, verify that the answer is correct to 5 decimal places. So this is just a slightly technical thing we need to think about. So I've got a number line, I've got 1.06568 that's to 5 decimal places. The next one up would be 1.06569 if it was going to round up to that. And then we've got the one below. 6, 7. So if we want to show that our answer is going to round to this, to 5 decimal places, we need to seek a sign change at these two positions. 1.06565, that's the midpoint between them. and then 1.065685. Because if we can get a sign change between these two, then we know the root is between these two. And if it is, then it's definitely going to round up from this direction or down from this direction. So I'm back to doing what we did at the start, using the sign change rule. It's a little bit frustrating it's making us do it again, but it does, like, the iterative method is great, but this like comprehensively shows that the answer is correct to 5 decimal places. Okay, so let's take a look at f of 1.065675 and then 85. Okay, maybe I should have just said answer equals so I didn't have to type it in twice. But I can also very easily adjust this one the second time around, or 3 times. Okay, hopefully I've typed that in right. So we get 9.1 times 10 to the minus 7, which is greater than 0. I didn't do that the first time. I think it's always good to just show that you understand that that's greater than 0. Okay, and just change all those 7s into 8s. A minus 2.9 times 10 to the minus 5. So we've just shown that at this point here where the red line is, it's positive, and here it's negative, so it must, at some point, we don't know how, at some point in between, it might not be exactly at this point. I should just, yeah, it could be like here, but it doesn't matter if it's here because it's still going to round to 1.06568 to 5 decimal places. Sign change. I don't think I need to write anymore. I can just say, so 1.06568. Okay, I know I've taken a long time going through this question. It took me a long time to make the video. It's quite technical and easy to make mistakes, and I'm trying to explain all aspects. So thanks for watching, and I hope you're happy with it now.